Very good morning, students. So, in this video, we are going to discuss about the electric lines of force. So, before the discussion of this electric lines of force, we have to know about the two different kind of the charges that we discussed already in the last video. So, once again, we are going to see the two charges. One is positive charge and another one is a negative charge. See the arrow marks. The arrow indicates that is nothing but it is electric lines of force. In the case of the positive charge, the electric lines of force are coming out from the positive charge. But in the case of the negative charge, the electric lines of force are coming towards the charge. Means the electric lines of force are starting from the positive charge and ending at the negative charge. This is general. Actually, this electric lines of force is a hypothetical concept. So, electric field, if you want to know from this means, it's nothing. It is a collection of electric lines of force that is called electric field. So, we can generate the electric field concept from this electric lines of force. Okay. So, if you want to know the detailed concept of the electric field means we should know about the electric lines of force. Right. So, see these arrows are nothing. It is electric lines of force here. For our convenience, I am giving the one positive charge and the arrows coming out from the positive charge and one negative charge and arrows coming towards the negative charge. So these arrows, this hypothetical representation of these arrows are nothing that is electric lines of force. And see these two pictures. In these, these two pictures are clearly illustrates about the concepts of the electric lines of force. See here, these two charges are positive charge. Means we know the basic property of the electric charge. Means if you bring the two positive charge, both charges will repel to each other. So the corresponding electric lines of force also repel to each other. See this picture. So this picture clearly indicates or clearly we can visualize the clear informations about the charge properties. One of the important charge properties, if you bring the two same charges, both will repel to each other. Here see the electric lines of force repel to each other, right? You come to this picture. Here we are keeping the two different charges, positive charge here and here negative charge. Hence, the electric lines of force starting from this positive charge and ending to the negative charge. Right? So, these two pictures clearly explaining the basic charge properties also. Right? Okay. So, when you go to the electric flux, that is nothing. It is a number of electric lines of force. Simply, we can call it as electric flux. Electric flux that is nothing but total number of electric lines of force crossing through the given area. See here now you consider the one area like this. It's a rectangular or square area. If you consider the positive charge, you consider the positive charge which are distributed on this surface of this area, and the electric lines of force are coming out from this in the both sides. Okay, coming out from this surface because we are considering the positive charges are distributed on the surface. That's why the electric lines of force are coming out from the surface of the plane, right? So in this, how many number of electric lines of force are coming out? That is nothing called electric flux. So electric flux, that is nothing total number of electric lines of force crossing through the given area simply. But suppose if you want to mention that the electric flux concept in terms of the mathematics means we have to notate, we have to represent that one like this. That phi, that is nothing. The phi is a electric flux. And what is that? E and ds. Now you come to this second diagram. In this second diagram, you consider the one small surface. It's a S surface. In this S surface, you have to consider the one small ds surface like this. Small surface. In this, you locate the charge, plus Q charge. Due to this plus Q charge, the electric field or electric lines of force. Consider here the electric field. Actually, what is the relationship between the electric field and the lines of force? Very simple. Collection of electric lines of force that is called electric field. So, electric field direction due to this positive charge is perpendicular to the surface. And one more point, you consider the what is the normal vector for this ds area. The normal vector, that always normal vector, you should draw exactly perpendicular to this surface, right? So the ds vector is represented in this diagram is exactly perpendicular to the surface, S surface. Now see electric field direction and ds direction. E means what? Electric field due to the positive charge. ds means that is a smaller area we are considering. Now you consider the direction of both E and ds. The direction of both are same. Hence, you have to use E ds cos theta or simply E dot ds because both are in parallel. No? If both are in parallel means if you take it, you have to take the dot product and you will get this one. So we may consider that what E ds means for here you see we are getting the electric flux for the smaller spherical area that is called d phi. So a smaller flux d phi that is nothing E dot ds. But I want to get the flux for the total surface. Very simple. Use mathematical technique. Use integration on both sides. What you will get? Phi is equivalent to integral over E dot ds. This is the final answer. What? This is a mathematical representation of electric flux. So, what is electric flux in terms of the mathematics? That is phi is equivalent to integral over E dot ds. Here you have to mention the one circle which indicates what? It's a closed integral. The surface is a closed one. It's a closed integral you have to use because it's a closed surface. And one more point, what will be the quantity? I mean, electric flux is a scalar quantity. This electric flux is a scalar quantity. And what is the unit for this one? That is nothing. Newton meter square per coulomb. How? We can derive that unit from this E into ds. E into s. Flux, I mean, sorry, field into area. We multiply it and what you will get? Newton square per coulomb. Newton meter square per coulomb. Okay. So based on this, now we are going to see one simple quiz. What is this? It's a very simple quiz. Which charge configuration produces a uniform electric field? There are four options given. Point charge, uniform, infinite uniform line charge, uniformly charged infinite plane, uniformly charged spherical plane. You consider the four charge configuration. Now we have to get the uniform electric field. What is the uniform electric field? It's a very simple collection of electric lines of force. Simply we may call it as a uniform electric field. What is exactly uniform electric field? Mean that is nothing parallel lines of force. That's all. Electric lines of force should be parallel for the case of the uniform electric field. Suppose if you are having the electric lines of force like this is not a uniform. This is uniform only in this region. That's all. Not in the whole. In this region, it is a non-uniform. Okay. So if you want to get the electric uniform electric field, mean that complete electric lines of force should be parallel. And in the given four charge configuration, which one will give the complete parallel electric lines of force? The third one, uniformly charged infinite plane. That is the correct answer. Right. See the first case, second case, and fourth case. All these three, point charge, infinite uniform line charge, and a uniformly charged spherical cell. In all these three, we will get the different electric field. That is, that electric field variation is due to the distance from the charge. If you consider the point charge, the electric field very nearest to this point charge is very high, but the electric field is very far away from this charge is less, right? Because of the less number of electric lines of force. Then how will you get the parallel lines? It is not possible in the case of the point charge, and similarly, it is not possible in the case of the uniform line charge and a uniformly charged spherical cell. It is possible in the case of the uniformly charged infinite plane. Plane means you may consider the plane like this. You may consider the charges which are distributed equally in all the places of this area of this surface, right? So if you consider the electric lines of force, the electric lines of force will come out from this charge exactly perpendicular to this one, right? That's very simple, right? So how many number of electric lines of force enter leaving this side, left side, and this right side? Both are same, right? And here, you consider the any one direction, any one side, left side or right side, all the lines will be in parallel, right? So this is possible. In this case, I mean, in the third case, we can get the uniform electric field. Okay. Okay, students, we will discuss like this topic in the next video.